One-dimensional motion. In this lesson, we'll be covering motion terms, scalar quantities, average and instantaneous speed, velocity equals distance over time, one-dimensional motion, vectors and velocity, displacement and position, as well as position time and velocity time graphs. Motion terms. The study of motion is called kinematics. Uniform motion is the motion of an object at a constant speed in a straight line. Non-uniform motion means movement which changes direction or speed or both. Check your understanding. Classify each as uniform or non-uniform motion and explain. A rubber stopper is dropped from your raised hand to the floor. So the stopper goes from point A to point B. Now this is non-uniform motion, and the reason for that is as the stopper falls, it accelerates downwards at a rate of 9.8 meters per second squared, or meters per second per second. This means that the velocity at the top, velocity 1, does not equal velocity 2, and therefore it's non-uniform motion. B. A car is traveling at a steady rate of 85 kilometers due west. The key word here is steady rate. Since it's steady rate, constant speed, constant direction, we're going to have uniform motion. C. A rocket begins rising from the launch pad. It's kind of similar to A. As the rocket goes up, the velocity at point 1, down here, compared to point 2, is not going to be the same. And the reason for that is because it accelerates. So now we're going to get an acceleration upwards, and since velocity 1 does not equal velocity 2, we get non-uniform motion. And D. A motorcycle rider applies the brakes to come to a stop. When we're applying the brakes, again, our velocity 1 will not equal velocity 2. We're going to slow down. We're going to accelerate in the opposite direction. Since we're slowing down, this is non-uniform motion. Scalar quantity. A scalar quantity has magnitude or size only, but no direction. So for instance, kilometers per hour, meters per second, kilogram, these are all scalar quantities because there's no direction. Vector quantities, on the other hand, have both magnitude and direction. So for instance, kilometers per hour west, or meters per second squared north 23 degrees west. So if it only has a magnitude, it's scalar, but if it has magnitude and direction, it's going to be a vector. Check your understanding. State whether the quantity is a scalar or vector. 9 milliseconds, that is going to be scalar since there's no direction. B, 3.1 meters up, that's going to be a vector because we have direction, up. C, 15 centimeters squared, scalar, no direction. D, there's no direction, just 500 hertz, so it's scalar. E, 113 kilometers per hour west, that has a direction, therefore it's going to be a vector. And F, 50 milliliters, it's a scalar because there's no direction. Average and instantaneous speed. Instantaneous speed is the speed at a particular instant. Average speed is the total distance traveled divided by the total time of travel. The symbol for average speed is velocity with an AV below it. The equation for average speed is going to be VAV equals distance over time, where D is the total distance traveled in a total time of T. V average, distance, and time. Since V equals D over T, we can rearrange the variables to solve for either of the other two. One equation now becomes 3. So we have our V equals D over T in our first equation. If we rearrange and solve for T, we're going to get T equals D over V, and then we can rearrange again to solve for D. D equals V times T. Check your understanding. A track star aiming for a world outdoor record runs 4 laps of circular track that has a radius of 15.9 meters in 47.8 seconds. So there's our track, and we're going to get a radius of 15.9 meters. We're told the time is 47.8 seconds, and he's going to do 4 laps. What is the runner's average speed for this motion? So first of all, what are our givens? Well, we have our first given is our radius is 15.9 meters. Now to find the distance is going to be the circumference of the track times 4. So to find the circumference of a circle, we do 2 pi r, and then we're going to multiply everything by 4 because there's 4 laps. So 2 pi times a radius of 15.9 times 4, and that's going to equal to 399.6 meters. What other given do we have? Well, we have time. We're told time is 47.8 seconds. Now, what's our unknown? Our unknown is going to be our velocity. That's our question. So velocity is going to equal to distance over time. We're told that the distance is 399.6 meters, and the total time is 47.8 seconds. And that's going to give us an answer of 8.36 meters per second. Now, the easiest way to know what the units are at the end is to actually put the units in your equation. So you have meters and seconds right there, and that comes up to meters per second in the answer. We have 3 sig digs in our answer because we have 3 sig digs there and 3 sig digs there. It's the lowest number of sig digs in the question, therefore we have 3 sig digs in our answer. Check your understanding. The record time for a particular race is 3 hours, 53 minutes, 17 seconds. So let's write that down. Time is equal to 3 hours, 53 minutes, and 17 seconds. Determine the average speed for this 42.2 kilometer race. So distance is 42.2 kilometers, and we're looking for velocity. Now we're looking for velocity in meters per second, and kilometers per hour. So we need to do one of them first, and then we can convert afterwards. So let's do it in meters per second. So let's make everything into meters and seconds. So distance is 42.2 kilometers, which is equal to 42,200 meters. The time, 17 seconds, we have that. 53 minutes converted into seconds is going to be 53 times 60, which equals to 3,180 seconds. And 3 hours is going to be 3 times 3,600 seconds, because there's 3,600 seconds in an hour. And that equals to 10,800 seconds. So our total time is going to equal to 13,997 seconds. And that's just going to take that guy, and that guy and add them together. And we have a distance in meters, so we're good to go. So velocity is going to equal to distance over time. The distance is 4,200 divided by 13997. And that's meters, and that's seconds. And that equals to 3.01 meters per second. And that's what we got here, so that's good. Now we need to convert that to kilometers per hour. So let's make a little space. So if we have 3.01 meters per second, and we need an answer in kilometers per hour, we're going to multiply this by 3,600 seconds for every 1 hour, and we're going to multiply it by 1,000 meters for every 1 kilometer. That's going to allow us to cancel out the meters and cancel out the seconds. So our kilometers per hour number is going to be 3.01 times 3,600 divided by 1,000, and that equals to 10.9 kilometers per hour. So that's our first answer, and that's our second answer. Linear motion in one dimension. Motion along a straight line is one-dimensional motion. This can be right, left, or up and down. So for example, the motion of a train along a straight line, an object like a ball falling freely vertically under gravity, and the vertical up and down oscillations of an object suspended from a vertical spring. Now this is different from uniform motion, which needs to have a straight line at a constant speed. Linear motion, on the other hand, just simply needs to have motion along a straight line. But as the example shows here, falling freely, that would be under influence of gravity, and in that case it's going to accelerate downwards at 9.8 meters per second squared. So we're not going to have a constant velocity as there's acceleration present. Velocity and other vector quantities. A vector quantity is a quantity with a magnitude and direction. We talked about scalar earlier. Scalar quantity is simply one with magnitude, but a vector has both magnitude and direction. So for instance, displacement and velocity are both vector quantities, and an example of a vector quantity would be 20 kilometers per hour east. The fact that it says east with our direction, that makes it a vector quantity. Distance and displacement. Distance is how far an object has traveled. This is the total distance. Displacement is how far an object is from its starting point, final minus initial. So the diagram below, the distance would be shown in red, right? Distance. And the displacement would be shown in black. That's going to be our straight line. So our straight line, final minus initial position. So in this case, the displacement, as I have written here, is 18, whereas the distance is more than 18. So in this case, I just did an example of 23 meters. Check your understanding. If you run around an oval track with a perimeter of 350 meters and end where you began, what is your distance? Well, if the perimeter equals 350 meters, then the distance is 350 meters. So distance, 350 meters. The displacement, however, if you go from here and you go all the way around the oval track and end up back here, well, your final position is going to equal your initial position. Therefore, your displacement is 0 meters. Velocity. So if you recall, average speed is the total distance traveled divided by the total time. Velocity is defined as the rate of change of displacement. So average speed is going to be our change in distance over time. But velocity is going to be our displacement over our time. Average velocity is the change of displacement divided by the time interval for that change. Now, that is the formula that we're going to do. And typically, if you're talking about speed, you might change this v to an s and say that s is equal to distance over time. Velocity, you're typically going to see it as d over t, as a displacement over time. Check your understanding. So again, we have our same track, but this time we have a little more information. So our perimeter is still 350 meters. So our distance is 350 meters. So if you run around an oval track in 10 minutes, so time, 10 minutes, and we know that there is 60 seconds per minute. Our minutes cancel out. 10 times 60 is 100, so our time is 600 seconds. So if you run around an oval track in 10 minutes with a perimeter of 350 meters and end where you began, what is your average speed in meters per second? Well, speed is going to be our distance over our time. The distance is 350 meters divided by 600 seconds. And that equals to 0.583 meters per second. Now we need 2 sig digs in our answer because 350 has 2 sig digs. So our final answer becomes 0.58 meters per second. Now B says, what's the average velocity? Well, velocity is going to be displacement over time. We just talked about on the previous question, the displacement in this case is 0. So 0 divided by any number is going to equal to 0. So the velocity is actually 0.00 meters per second. And then we need a direction, so it would be around the track. So I'll just put it over here. So velocity is going to equal to 0.00 meters per second. And then in brackets, we'll just call it around the track. Check your understanding. A cyclist takes 25.1 seconds to cover a displacement of 115 meters east from D1 to D2. So let's draw it out first. So D1, D2. And that distance is 115 meters. Now the time to complete that is 25.1 seconds. So for A, calculate the cyclist's average velocity. So velocity is going to equal to displacement over time. The displacement in this case is 115 meters, and the time is 25.1 seconds. So that gives us a velocity of 4.58 meters per second east, as we're told that it's east in the question. B, if the cyclist maintains the same average velocity for 1 hour, what is the total displacement? To find displacement, we need to rearrange our equation. So displacement is going to equal to velocity times time. The velocity we found was 4.58. That's actually 4.582 meters per second times 1 hour. And then let's put that into seconds. So we're going to do our conversion. 3,600 seconds per 1 hour. Hours cancel out. So you're left with 4.582 meters per second times 3,600 seconds. And that gives us 16,494.0 meters. We need 3 sig digs in our answer. So it's going to be 16500 meters or 16.5 kilometers. Now C, if the cyclist turns around at D2 and travels 565 meters west to position D3 in 72.5 seconds, what is the average velocity for the entire motion? So let's make a little bit of space here. We're going to need to add to our drawing. So it turns around at D2 and travels 565 meters west. Let's make our compass here, east, west. So 565 meters. Now, the question asks for what is the average velocity? So velocity means we're going to need to have displacement. Now to find displacement, that's final position minus initial position. So our final position is actually going to be this 565 minus the 115 meters that they traveled initially. Another way to look at it is if we state west as positive, we're going to have 565 plus negative 115 because that was east. Now 565 minus 115 is 450 meters west. Now the time to do this is 72.5 seconds, but that isn't the total time. We need to keep in mind that first he went east, then he turned around and went west. So the total time is going to be 72.5 seconds plus 25.1 seconds. And that equals to 97.6 seconds. So now we're ready to do our answer. So for C, V equals D over T, 450 meters divided by 97.6 seconds. And that equals to 4.61 meters per second west. And that's our final answer for C. Now, why is it west? Well, our final displacement was west. Right? We went east first and then we went west, so our resulting displacement is west. Therefore, our resulting velocity is west. Check your understanding. Now, at this point, I want you to pause the video, go through questions 1 to 5, write out your answers, commit to an answer, and then we're going to go through it. Okay, so let's start at number 1. Is it possible for the total distance traveled to equal the magnitude of the displacement? If no, why not? If yes, give an example. Well, let's just take, for instance, if we have a starting point here and a starting point there, and we go like that. Now the displacement would be a straight line. Now the displacement would be the straight line, and the distance would be the squiggly line. Now in this case, the distance will be bigger than the displacement. The best case scenario is if you go from point A to point B in a straight line, then in this case, the distance will equal the displacement. So the question says, is it possible for the total distance traveled to equal the magnitude of the displacement? Yes. Number 2, is it possible for the total distance traveled to exceed the magnitude of the displacement? Well, as we just showed in our example, the distance here is much bigger than the displacement. So yes, it is possible for the total distance traveled to exceed the magnitude of the displacement. In fact, it will always exceed the displacement except when it is equal to it. Number 3, is it possible for the magnitude of the displacement to exceed the total distance traveled? No. So it is not possible. As you can see in our example, if they were exactly equal, if the distance was in a straight line and therefore the displacement equaled the distance, that would be the closest it can come. The displacement can never exceed the distance traveled. It can only equal it or be smaller than the distance traveled. Number 4, can the average speed ever equal the magnitude of the average velocity? If no, why not? If yes, give an example. Well, yes. Speed here is going to be our distance, and our velocity is going to be our displacement. Since they're both located on the same part of the equation, both above the time, and we know that distance will either equal to or exceed displacement, our numerator will be bigger, therefore our right side will be bigger or equal to, right? It could be distance could equal displacement, so in that case, then it would be the same. But assuming our distance is bigger, that's going to make our numerator bigger, which is going to increase our speed. So since our distance is bigger or equal to our displacement, our speed can either be equal to or greater than our velocity. So can the speed ever equal the magnitude of the average velocity? Yes, it can. Number 5. A truck driver reacting quickly to an emergency applies the brakes. During the driver's 0.32 second reaction time, the truck maintains a constant velocity of 27 meters per second forward. What is the displacement of the truck during the time the driver takes to react? Let's just say that that is forward, and we're going to call that positive. What else do we know? We know that the time is 0.32 seconds, and we know that the velocity is 27 meters per second forward. We're asked, what is the displacement of the truck during the driver's time to react? Displacement is going to equal to velocity times time. Velocity is 27, time is 0.32 seconds. So we get a displacement of 8.64 meters per second forward. We have 2 sig digs in our question, therefore our answer is going to have 2 sig digs, and it comes out to 8.6 meters per second forward. Displacement and velocity graphs, uniform motion. These graphs visually show us the motion of an object. For instance, this table, this graph, and this graph all show us the motion of the exact same object at the same time. Displacement time, dt, and velocity time, pt graphs. So have a look at the graphs below. They represent the same situation. So if we take a look at this graph, this is a displacement time graph, and this one's a velocity time graph. And they're actually showing the exact same information. And if you take a look at the slope of the dt graph right here, what do you think it tells you? How does it look? What does it remind you of in terms of the velocity time graph? So pause the video, have a look, and see if you can see how they're connected to each other. So how exactly do they relate to each other? Well, the slope of the dt graph is actually equal to the velocity in the velocity time graph. And we can see this. So if we take rise over run, I'll just pick 2 points. So let's take this point right here and this point right there. So in this case, we're going to get a rise of 400, and we're going to get a run of 80. And if you do 400 divided by 80, you get 5. And you can see our velocity time graph, it's actually 5 as well. And it does make sense. Velocity equals displacement over time. And that's what we're doing here, right? The rise is the displacement, which is our 400, and the run is the time, which is 80. So 400 divided by 80, the rise over the run, is the displacement over the time, which equals the velocity of 5. And this is what we were just talking about. So the slope of the dt graph describes the average velocity of the vt graph. Check your understanding. So pause the video and describe the motion for the graph below and sketch the corresponding velocity time graph. So have a look at this motion as described by this displacement time graph, and see if you can figure out the motion of the object and then draw the corresponding velocity time graph. So what we see when we take a look at the graph is that the slope of the line is constant. So what is the slope of the graph? Well, we can figure that out, right? Slope is rise over run. In this case, it's actually going west, and it's going down. So our answer is going to actually be in east. But we can take a look at the rise over the run first. So the rise, let's take this point, and we'll take this point. So in this case, the rise is 60 over 6. 60 divided by 6 is 10. It's meters, so that's the rise, per second. So we get meters per second. We're becoming less west, so we're actually going east. So the slope of the line is constant and is negative. As we just picked out, it was 10. This means the velocity is constant in the easterly direction. So we have easterly direction at 10, and that's what we figured out the slope was going to be. The initial position is away from the origin, and the object is moving towards the origin. Now, how do we know it's moving towards the origin? Well, the displacement at the origin is actually going to be 0, right? And since it's going towards 0, we know it's going towards the origin. As our direction is west, and it's becoming less west, we know it's going towards the origin, and it's traveling in an easterly direction in order to get there. dt and vt graphs continue. Vt graphs also tell us about displacement. So if you recall our equation for average velocity, so this is bottom left right here, if we rearrange it, we can find displacement. Displacement equals velocity times time. So using a velocity time graph, we can determine the displacement during any period by multiplying the average velocity by the time interval. As we picked out, our equation is velocity times time. We know what the velocity is, and if we pick a time interval, we can figure out what the displacement was during that time. So let's just say we picked time 1 to time 2. So in this case, we're getting a velocity of 7, because it's constant during that time, times the time, which was 1. So in this case, the displacement would have been 7 meters. Check your understanding. Find the area under the line between times 4 and 6 seconds. So here's time 4, and here's time 6. There's our velocity. There's our time interval. So the area underneath is right there. Now how do we calculate area? Well, in this case, area is going to equal to velocity times time. The velocity is 7. The time is 2 seconds. So we're going to get 14 meters east. Keeping in mind that displacement is a vector quantity, vectors need to have a direction, and we're told here the velocity is east. So our final answer becomes 14 meters east. Check your understanding. A military jet is flying with uniform motion at 9.3 times 10 to the 2 meters per second south. At time 0, it passes a mountaintop, which is used as a reference point for this question. A. Construct a table showing the plane's displacement relative to the mountaintop at the end of each second for a 12-second period. Pause the video and draw your table. So you can see the table we have drawn. We go from time 0 to time 12, counting up by 1 second, and you can see our displacement increases by 930 every time. So this is 930 times 1, 930 times 2, and so on, all the way down to 11,160. B. Use the data from the table to plot a displacement time graph. So pause the video at this point and draw your displacement time graph using the information in this table. So here's our displacement time graph. We're going south, so make sure you have south in your title. Time is along the x-axis, and you can see how we go up by time of 1 second, we get an increase of 930. You can see every time we go up by a second, we increase our displacement by 930 meters. After 2 seconds, we're just under 2,000, and so on, and it's going to relate exactly to our table. So after 2 seconds, it was 1860. After 6 seconds, it was 5,580, which is about right there. So your graph should look something like this. C. Find the slope of the line segment on the displacement time graph. Is the slope constant, and what does it represent? So pause the video and answer these questions. Now the slope, as we've been talking about, is rise over run. So you can pick any 2 points, but in this case I took points 0 and points 12. So the rise in this case is the full 11,160, as we can see in our table. So we have 11,160 divided by time, which was 12 seconds, and that gives us 930. Now what does this represent? Well, the slope represents the average velocity of the plane. D. Plot a velocity time graph of the plane's motion. So I want you to pause the video and plot the velocity time graph for the plane. Okay, so here's our graph. You can see we have velocity in meters per second south on our y-axis, time on our x-axis, and we have our slope of 930, and it goes straight across because we have constant velocity. E, calculate the total area under the line on the velocity time graph. So that is going to be a box that looks like this. So you need to calculate the area under that. So I want you to pause the video and answer this question. So the area underneath this box is going to be velocity times time. 12 seconds times 930 meters per second is going to give us 11,160 meters. We need 2 sig digs in our answer, so it comes out to 1.1 times 10 to the 4 meters. And it would also be correct to say 11000 meters. That would also be correct. Now, since we're talking about displacement, we need to have a direction. We went south, so we should have south as your direction. F. What does this area represent? So pause the video and write down what the area represents. The area under a VT graph represents the plane's displacement during this time. And that concludes our lesson on one-dimensional motion.